Hi, my name is Pichojai Varujan, and I'm going to talk about the topic quaternions. Let's start. So, look at these pictures. What do these things have in common? Actually, they all rely on a mathematical concept of quaternions that extends beyond the familiar dimensions of 2 and 3D. But what are quaternions and why are they so important? For now, you just imagine you're holding a toy airplane. You can tilt it up and down, turn it left and right, and roll it sideways. That's three different ways to move it, right? But what if you want to describe exactly how the airplane is turning all at once super smoothly? That's where quaternions come in. So let's explore it deeply together. First of all, we have to know about the quaternions' origin. The realization of the concept of quaternions is a really interesting story. The story of quaternions is not just a chapter in math history, it's a true sensation, really. It all began in 1843 with an Irish mathematician, William Rowan Hamilton. This person actually, he made a dramatic opening that he immediately carved into the stone of the bridge on his way to the Royal Irish Academy with his wife. But what he carved into the stone? Here, as he walked by on the 16th of October 1843, Sir William Rowan Hamilton, in a flash of genius, discovered the fundamental formula for quaternion multiplication. I squared equals to j squared equals to k squared equals to ijk and equals to -1. Cut it on the stone of this bridge. Yes. Before we dive deeper, let's quickly recap what real, imaginary, and complex numbers are. So here we have the equation x squared is equals to 9, and there are two roots that possible. First is equals to 3, and second is -3, because we know that -1 squared is equals to 1. But why we have the equation x squared is equals to -9? Like before, when we saw this kind of problem, we stopped at the moment when we realized that it is impossible to find x, right? Like when its square is equals to negative number, in that case, you say that there are no real solutions. And here, the keyword is real, because it has meant that there are other solutions that are beyond the real numbers. Here in 1637, René Descartes proposed that such solutions weren't real but imaginary. This idea took off when Euler formally defined imaginary numbers, and later Gauss introduced complex numbers, which is combination of real and imaginary terms. And look at here, y-1 squared equals to -9, and it also have two roots, which is complex. First is 1 plus 3i, and 1 is minus 3i, because we know that it's equal to root of -1, right? And also we can interpret the complex numbers in Argand diagram, like here, knowing the real part, which is x-axis, and imaginary part, which is y-axis. So, fascinated by complex numbers, Hamilton started to think about expanding the theory of couplets to a new theory of triplets, or something with a real axis and two imaginary axes, I and j. Also here, in his letter from Hamilton to John Graves about quaternions, he describes all of his work. That first he opens the new 1j, but then he forced to apply a new letter k. So why? Because, we know the multiplication of I to I is equals to -1. But what's I to j? Like here, he really was confused about this multiplication. Is it equal to 1, -1, or 0? He just came to the idea that there is another imaginary part, k, which shows the multiplication of I to j is equals to k. And this breakthrough not only solved Hamilton's puzzle, but opened the door to 4D mathematics, revolutionizing how we think about rotations in space. Now we can think about the quaternions itself. So if Hamilton extended one imaginary part to 3, it does mean that we have this kind of formula: a plus bi plus Cj plus dk, like three imaginary parts, I, j, k. Also, you have to know that this can be represented in 4D, like this sphere. You see, like this axis is equal to I, this to j, this to k. Here you see this fundamental quaternion formula, which also Hamilton carved into his stone. And we have to know that I, j, and k are fundamental quaternion units. According to Hamilton's famous expression, there is a relationship between I, j, and k. This is a definition of quaternion multiplication. And there exists a special right-hand rule that helps to understand this relation. But it's really hard to remember it, and also for me, I have the easiest way to remember this multiplication rule. Just imagine that you have this I, j, and k, three imaginary units, and you have to just imagine this circle, like from I goes to j, from j goes to k. When you multiply I to j, it equals to k, and it goes to anti-clockwise, the sign of the multiplication result will be plus. But when it goes to clockwise, it will goes to the result with minus. Like here, j to I equals to minus k. And also here with coordinate system, with three these quaternion units, three axes, right? And we see like this I, this j, and this for k. So actually it means rotation. Just see, in the center we have 1. I multiplied to 1, it equals to I, right? But I multiplied to j, it equals to k, we know it. And I multiplied to k, it equals to minus j. And it goes like this circle. And it also shows this relation. First one is addition and subtraction. You can say I, j, and k as x, y, z. Like just equation, and we just add or subtract real parts and then imaginary parts with this component wise, like I to I, j to j, k to k. It's really easy. But with scalar multiplication, it also have to be easy because when we multiply one real number to the quaternion, we just multiply each quaternion to this number. And we interpret this to I as a one real number. Like we just ignore the parts I, j, and k and just multiply these numbers before imaginary units. So what about conjugate and norm? We know these terms from complex numbers, right? And it's similar with quaternions. Like the quaternion conjugate can be computed by negating the vector part of the quaternion I, j, and k. And its norm, it equals to roots. And you just square each part of the quaternion, just ignoring the I, j, and k part. And about the quaternion products, we just take one and multiply to each part of the second part of the products. And then you take 4i and multiply to each, to 3, to 5i, to 9j, to 7k. And the most important part here is when you multiplying I to j, you use these formulas. You have to know about these formulas and this. Like here, 4i multiplying to 9j, we know that 4 to 9 is equal to 36. But I to j, you cannot write just ij. You should write k because we know these formulas and we can just simplify it. Now, the most interesting part is applications of quaternions. And as you recognize at the beginning of this presentation, I mentioned some applications of quaternions with pictures of drone, video games, such that. But it is the small part of their usage. So let's try cover most of real world uses and understand them. Okay. The first one is aircrafts and rockets. Have you ever wondered how planes stay stable in the air or how rockets adjust their orientation in the vastness of space? The answer lies in quaternions. It is also useful for aircraft and rockets. So you remember my example at the beginning about the toy airplane, like we can tile up, down, etc. So it's orientation, how it tiles, turns, or rolls. So engineers traditionally represented these rotations using three arrays of numbers called matrices. First, imagine you are balancing on a spinning chair. You can tilt forward, lean sideways, or turn the chair around. But if two of those movements align, you lose 1 degree of freedom. It's kinda some physics stuff, but it's fact. And you're stuck in a limited range of motion. In aircraft or spacecraft, this kind of alignment can lead to catastrophic failures in navigation. Unlike matrices, quaternions avoid this problem entirely. Instead of breaking rotations into three separate movements, quaternions describe them as a smooth, unified operation in 4D space. By using quaternions, modern aircraft and spacecraft can perform precise and stable rotations. And this technology is essential for drones also. So these drones that hover steadily in the wind, rockets that need to adjust their trajectory in space, and spacecraft that rely on exact movements to dock or land. That means quaternions simplify rotation, improving precision and performance. That's why it is used in robotics, especially for drones. And our third application is computer graphics and animation. In computer graphics and 3D animation, quaternions ensure characters and objects move naturally, with no sudden jumps or awkward angles. Whether it's a humanoid turning its head or bird flapping its wings, quaternions provide seamless movement. Key drawing technique was used at first traditionally, and then computer graphics of 3D objects started to work by key positions using principles of quaternions to rotate the object. And next, as we talked about the computer graphics, it is really logically that we have application in video games. Since video games use 3D animations, in the game are constructed via graphics. Like here in graphics, you can say that these characters are made in 3D. And our last application, and maybe important one, is space exploration. So quaternions enable precise control of spacecraft orientation and solving problems that traditional methods can't handle. In space exploration, we need our spacecraft and satellites, which help us to explore the cosmos. Spacecraft don't just travel in a straight line, they need to orient themselves to perform a variety of critical tasks. All these tasks involve rotations in 3D space. It is similar with aircraft and some drone, but here we have to pay attention to for space conditions as it is not similar to air. So for example, satellites use quaternions to align their solar panels with the sun, maximizing energy captures, like it really matters, and to position their antennas toward ground stations for communication. And as a conclusion, I can say that quaternions allow humanity to explore worlds, study the cosmos, and expand our understanding of the universe, all with incredible precision and efficiency. Without quaternions, many of the technologies we take for granted, like reliable air travel and space exploration, would face significant challenges. So, yes, that's the end, and thank you for your attention.